Okay, so recording. Let's do some stuff. Oop. Okay, so first we got what is G13? So I go to G. I look for row row one, column three. That's right there. So it's one. First number is row, second number is column. So row one, column three. And then what is E64? Well, that's not possible. I know because it's not possible. Because if I look at E, I only got three rows, so you wouldn't be able to do six. And then I only got two columns, so you wouldn't be able to do four. Okay. All right, or undefined too, you could say. Um, it's not possible because there aren't six rows or four columns. Now find a determinant. If I got a matrix that looks like this, then the determinant is A times D minus B times C. So if I want to know what the determinant of A is, so this is my matrix right here. So I'm going to take 1 times 1 minus 2 times the negative 3. How'd I get what? Go ahead, it's okay. Yeah, that's why I wrote the matrix that I'm talking about, A right here. This is general. Uh, 1 minus negative 6 or 1 plus 6. So the determinant for this one is 7. Yeah, it's not always negative. I'm saying, what are you confused about? What are you confused about? Yeah, I'm saying A times D minus B times C. Yeah. How about we talk about that when I'm not recording? All right, so create a 3 by 3 identity matrix. Well, 3 by 3 would look like this. Ones along the diagonals, everything else is 0. So along that diagonal right there, you get all ones. No, it matters. It needs to be if for the identity matrix. It needs to be one, and they need to be a square, so the same amount of rows and the same amount of columns. That's the identity matrix. I'm just explaining. You saying where I get the numbers from? I'm saying it's the identity matrix. This is the answer to that one. I'm just giving you examples of other ones. This is a 2 by 2 identity matrix. Yep. And this is a 4 by 4 identity matrix. The identity matrix is just ones and zeros. Okay. It's ones go along that diagonal. Everything else is a 0. So that's a 3 by 3. That's a 2 by 2. That's a 4 by 4. Hmm. Now the question just said give me a 3 by 3. So I was just showing you examples of other ones. Okay. Excuse me. Okay. So now I got 2 times G minus 3 times H. So these numbers are scalars. They get multiplied. They multiply all the numbers in your matrix. So 2G is just 2 times everything in G. So that would be, let's see, 2 Whoop, come on, man. Making me look bad. Okay, that would be 202, 6, -2, -4, 0, 4, -2. So that's 2G minus, and then I got, you know what? We could do it a different way. Let's do it like this. Let's say we're going to multiply -3 times everything. Or is that too confusing? Okay, let's just do regular, please. So now I got to do 3H. So 3 times everything at H. So that's 3, 6, 9, 6, 9, 3, 9, 3, 6. And then I need to subtract each element from its corresponding element. Yep. 0 minus 6 is -6. 2 minus 9 is -7. 6 minus 6 is 0. -2 minus 9 is -11. -4 minus 3 is -7. And then finally, 0 minus 9 is -9. 4 minus 3 is 1. And -2 minus 6 is -8. 4 minus 3. Where we're at? Well, I'm saying which ones? Right here? That's a 4, man. And then C minus W. Okay, here's the thing. When you add or subtract matrices, the dimensions have to be exactly the same. They're not, so it's undefined or not possible. Okay, I can't help you if you don't remember. That is, you count how many rows they got and then how many columns. So that's the 2 by 3. That is, yes, they have to be exactly the same. Yes, yep, we're getting to that. But yep. So this is not possible. Can't do it. All right, now F times A. F is -5, 2, -1, 3, 4, -4. So how many rows and then how many columns? This is a 3 by 2. And then A is 1, 2, -3, 1. That is a 2 by 2, right? And so like you were saying, the inner dimensions are what have to match on this. And the inner dimensions do match. So my result should be a 3 by 2. So I should have a matrix that looks similar to that. All right. And I'm running out of room, so I'm going to go down here. What? I am answering. I said I'm just moving down because I was running out of room. So what I need to do is I'll multiply a row times a column. See how there's two numbers going across and then two numbers going down, so they match up. So to get that first row, let's see. I've got -5 times 1 plus 2 times a -3. That's my first element. And then to get my second element, it's -5 times 2 plus 2 times 1. So that's my first row. And then my second row is -1 times 1 plus 3 times a -3. And then over here, I've got negative 1 times 2 plus 3 times 1. And then my final row, that's 4 times 1 plus a negative 4 times a negative 3. And then I've got 4 times 2 plus a negative 4 times 1. Excuse me. So now I got to start working this out. So negative 5 times 1 is negative 5 plus 2 times negative 3. So that's negative 5 plus negative 6. So that's negative 11. Matter of fact, let's just write it. Negative 5 plus. Hey, what's up? Yeah. You're not going to take nobody else? That's messed up. Okay, so ne- dang it, I can't pause it. Okay. Well, anyway, negative, like I said, that's negative 11. Well, I got to think about how I want to do this. Yeah. So then I've got negative 10 plus 2. Okay, so that's negative 11 and that's negative 8. All right, so next I got negative 1 times 1, so that's negative 1 plus I got 3 times a negative 3, that's negative 9, so that's going to be negative 10. And then I have negative 1 times 2, so that's negative 2 plus 3 times 1, so that's 3. Negative 2 plus 3 is positive 1. Excuse me. Thank you. So 4 times 1 is 4. Excuse me. Negative 4 times a negative 3 is positive 12. So that's going to be positive 16. And then I've got 4 times 2, that's 8. And negative 4 times 1, that's negative 4. So that's positive 4. So here's my answer. Negative 11, 8. Negative 10, 1. 16, 4. All right. I'm going to go back to this right here, C times D. If I look at C times D, they're exactly the same type of matrix. That's a 2 by 3 times another 2 by 3, and you can't do it. That defies the rules. Sorry. Yep, pushed the wrong button. Yeah, that's NA or not possible. This goes with that. Okay. Well, hold on. It's that's kind of tricky to say. Hold on. It's not just automatically the same. This is a 2 by 3, and then this, what is it? D negative 1, 0, 4, 3, 1, 1. It's because the inner dimensions don't line up. See, 2 by 3 and a 2 by 3. If it was a 2 by 2 and another 2 by 2, the inner dimensions line up no problem. If it was a 3 by 3 times another 3 by 3, you could do that. But when you got different numbers like that and you're taking the same one, it's not going to work because the inner numbers need to be the same and they're not. One's a 3 and one's a 2. So this is not possible for undefined. I'm sorry about the way that looks. Not available, which I'm okay with that. Not possible or undefined. That's this one right here. I used all the space to do this problem. I ran out of space for this one. So because it is a 2 by 3 matrix times another 2 by 3 matrix, the inner numbers don't match. See up here with F times A, the inner numbers matched. See, I had a 2 on the end of the first matrix and a 2 at the beginning of the second one. The inner dimensions match, so you can multiply them. But with C and D, you can't. Eh. Yeah, well, I'm gonna try to make sure that's not the same case. So anyway, describe the geometric effect of the transformation on a 3 by 3 identity matrix given by the following matrices. So this right here, this is a dilation with a scale factor of 1/2. All of the stuff in my matrix gets multiplied by 1/2 is what that means. Okay. Yeah, that's the answer. They want to know the geometric effect. It's a dilation with a scale factor of 1/2. Yep. A dilation is either a stretch or a shrink. It's either getting bigger or smaller. So anyway, this right here is a reflection about the XY plane. See, this first one represents X, the second one represents Y, and the third represents Z. So when I'm looking at the identity matrix, all ones going this way. If one of them is negative, it makes a reflection about the other two. So, so like if the first one was negative, it'll be a reflection about the YZ. Excellent, ma'am. If the first one was negative, the X was negative, it'd be a reflection about the YZ plane. I'll say again that if I'm looking at this matrix the way it is, the first column is X, the second column is Y, the third column is Z, right? So if I have an identity matrix, all ones, they go down the diagonal, but one of them is negative. That's a reflection about the other two. So like right here, this represents a reflection about X and Y. And let me see if I can draw this a little plainer because it looks a little scruffy. So if I have an identity matrix that has a -1 as the first element, oops, that's a 0. So this one right here will be, the X is negative, so it would be a reflection about the YZ plane. All right? Yes, no, no, yes, what's up? Any questions? All right, fun stuff. All right, changing stuff from complex numbers to polar coordinates. I need to remember a couple things. Let me see. Rectangular. Oops. Rectangular coordinates go x plus y times I. Polar coordinates go r times cosine theta plus I times sine of theta. So if I'm going from rectangular to polar, I need to find out what r is, and I need to find out what theta is. Those are the two things I need to find out. And I use the x and y that I have to find them out. So r equals the square root of x squared plus y squared. And then theta is the inverse of tangent of y over x. So let's see, what do I got? So I need to figure out r. Well, my x for this is -5 and my y is +5. So I'm just going to plug and chug into this thing. So r is going to equal -5 squared plus 5 squared. So that's going to be 25 plus 25 square root. And it's going to be the square root of 50. which is 5 square root of 2. All right, now I need to get the tangent. So I need to inverse the tangent of, and then I just put y over x. So that's 5 over negative 5. Or to inverse the tangent a negative 1. Nope, I don't. Not one memory of it. That's what it should be. Yep. So I'm gonna explain. I know exactly what you're talking about. Just a second, I'm call myself trying to do this. So the inverse of tangent. Oof. Of negative 1. So that's negative 45. Now, the thing is, I want you to change the angle to its radian. So you need to know how to change radians to, or degrees to radians. So this is going to be negative pi over 4. Nope, it's pi over 4. All right, so now I got all the components I need. So my answer is going to be 5 times the square root of 2 times cosine of negative pi over 4 plus I sine. You need to change 45 degrees to radians. You need to know how to do that. And we can cover that because I got it in the question a little lower. So we can go over that again. Minus pi over 4. And that's why I'm trying to think about how I'm going to do it. Ah. It's just tedious. So now I got to do this one. So the next one is, so I need R. So R is 2 square root of 3 squared plus negative 2 squared under the square root. So 2 times the square root of 3 squared ends up being 4 times 3, which is 12. And then negative 2 squared is 4. Matter of fact, let's do it right here. So that's the square root of 16 or 4. So R is 4. And then I need my theta, which is the inverse of tangent of negative 2 over 2 times the square root of 3. And that's going to be negative 30. And negative 30 changes to negative pi over 6. And then finally, I need to just put the stuff in order. So 4 times cosine of negative pi over 6 plus I times sine of negative pi over 6. And that's my answer. Let's see, do we have enough time for one more? Sure. Okay. Now I got to use polar coordinates to graph something. So the second thing is degrees or angles. Sorry, not degrees there. It's, you know, for each one of those hash marks is 15 degrees or it's pi over 12. So anyway, 4, that tells me where I'm starting at. So positive 4 tells me I start right here. So that's my starting point. And then I need to go 75 degrees. Let's see, 15, 30, 45, 60, 75. So that puts me right here. It's just going to be a dot right here. That's my answer. I don't have to. Positive is this way, negative is that way. Negative, as far as where your starting point is, this is negative on the left. This is positive on the right. So then let's look at the next one. All right, so -1 is right here. This is my starting point. And then -2π/3. Well, it'd be nice to know how many steps 2π/3 is. Well, how many steps? I can look right here. 1, 2, 3, 4, 5, 6, 7, 8. It's 8 steps. But it's going negative, so it's going this way. So I go 1, 2, 3, 4, 5. Wait a minute, shoot. 1, 2, 3, 4, 5, 6, 7, 8. It's right here. Right here. 1, 2, 3, 4, 5, 6, 7, 8. Yep, right there. Because we're going in negative direction, we're going this way. How'd I get what? Because if this is positive, going from 0 to 2π/3, I just counted how many steps went that way. 1, 2, 3, 4, 5, 6, 7, 8 to get right here. So then if I'm going the opposite direction, I just count 8 the other way. 1, 2, 3, 4, 5, 6, 7, 8 along this line. But my starting point was right there at -1, so that's where I am. And let's see. So right here, so when I'm dealing with these two special triangles, I've got the 30, 60, 90 triangle. Okay, I got the 30, 60, 90 triangle that gives me a triangle that goes in this pattern. This is 30 and this is 60. Then this direction, give me a letter, Prince. Okay, so this is T. This is T times the square root of 3, and this is 2T. Well, in this case, I know what this thing is. Yes. So I know that T times the square root of 3 gives me 6. So I can figure out what T is by solving this equation. So I'm going to divide both sides by the square root of 3, and I get T equals 6 over the square root of 3. But the thing is, you can't have the square root in the denominator. I need to rationalize. So I'm going to take 6 square root of 3, and I'm going to multiply top and bottom square root of 3. And that's going to give me 6 square root of 3 over 3. Now, to show you the steps more, that's 6 square root of 3 over the square root of 9, which is 3. So that's 6 square root of 3 over 3, but then I can reduce. 6 divided by 3, so T equals 2 square root of 3. Well, T is in the same spot as my Y. So Y equals 2 square root of 3, and then 2T is going to be 4 square root of 3. Now this one, this triangle, 45, 45, 90. So give me another letter, Prince. Okay, so these two sides are V, and this side is V times the square root of 2. Well, I look at what I got. I got 11 in that spot. So I say 11 equals V times the square root of 2. And then I divide both sides by the square root of 2. And I get V equals 11 over the square root of 2. But like I told you before, I can't leave it like this. I need to rationalize. So I'm going to say V equals 11 over the square root of 2 times the square root of 2 top and bottom. So I get 11 times the square root of 2 over 2. And I can't reduce that any. So y equals 11 square root of 2 over 2, and x equals 11 square root of 2 over 2. All right, and we can call that. And